Okay, so the last time I want to press continue here. We were trying to do something that the idea is that we don't know where we're getting at, and so let's revise what was going on. Let's focus on a group. Okay, I think it's like more famous here. So okay, let's focus on a group, and let's say I have a group. So it's a group G, and I want to see what I can infer if I have an arrow, and since let's think I'm in the category of groups. So which is the codomain of this arrow I'm thinking about? It's the endomorphisms of some object X in some other category. No, actually, let's say monoid. Sorry if you like groups. It's it's better if I start with monoids. Okay, so you have a category C. I don't know which category it is. You pick an object X. I don't know which object you like, but definitely, if you look at all the endomorphisms of X, so here is X, and here are the endomorphisms of X. These things, the yellow things, form a monoid under composition and identities, which means that if you have another monoid, like M, you can have a monoid homomorphism from your monoid to the yellow arrows. And you map the operation of the monoid to the composition of these yellow arrows, the identity obviously to the identity, and that's it. And if you write down the laws of what this thing needs to satisfy, it's those things. So your arrow is the row arrow, and the idea is that it has to respect compositions, which I wrote like that. It maps the operation of the monoid to the operation of the yellow monoid, which is composition of arrows, and it has to map the identity of the monoid to the identity arrow of this X. Okay, so good so far, I hope. Now, if you like upgrade or downgrade, this is a matter of point of view, from monoids to groups, what happens is that you can no longer look at all the endomorphisms because you would like to take care of the inverses that you have in a group. So you say, okay, I will look at the automorphisms of X, because now it's like not all the arrows from X to X, but only the invertible ones. And now if you limit yourself to these ones, you can map a group, you can have an homomorphism from a group to these arrows. And I hope this makes sense as well. And if you write down the laws, you'll get this extra law which says that, okay, if you take the inverse inside the group of an element R and you apply a row to it, then it's the same thing as if you first apply a row to the element and then invert the arrow, right? This is like the inverse arrow from these arrows. And eventually, I think it was Sotiris who said, okay, but no, maybe not, I don't remember, who said, what about rings? And I cannot do further stuff here because I don't have an extra operation with this here, a binary operation among these arrows. It's like only composition. So what happens is, if you say, okay, let's fix a different category. I said you can pick any category you like. Let's pick a category that its elements carry some structure. So let's pick, for mysterious reasons, let's pick the category of abelian groups, commutative groups. Okay, so now what happens is that X, I know what kind of thing X is. It's an abelian group. And this means that all arrows in this category, including the endo arrows that go from X to X, are group homomorphisms that respect all the group structure, and X happens to be a commutative group. Why does that thing change anything? So the exercise that you were supposed to solve is this one, prove, and the idea is that if you have any homomorphism between groups and the codomain is abelian, then you can define this function here on the homomorphisms of groups. Give me two homomorphisms and I will define the sum of these homomorphisms to be this thing. It's the homomorphisms that picks an A, applies the first homomorphisms to A, the second, okay, that's a mistake. The second homomorphism to, okay, that's the two mistakes. The second homomorphism to this same element, and then since you have applied phi and a, you have a here, you have applied phi, and you are in phi of a which lives in B, and remember B is an abelian group, and now you also apply psi, and now you are in psi of a. It means here is phi of a, here is psi of a. It means you can add these using the operation of B, and you can have phi of a plus in B of psi of a. And you name this thing, this is where you map in this element, I don't know, maybe it's this one, you map, you say that these homomorphisms that you are defining right now will map A to this thing. Are we with me? Are we? Okay. So, there's something you need to prove. You essentially need to prove that this thing is indeed an homomorphism. So, okay, very quickly, you realize why I need the codomain to be an abelian group. What do I need to prove? Essentially, to prove that it's an homomorphism, it needs to respect everything. But if you remember, there's a criterion that says, okay, among groups, if you respect the binary operation, then you gain the other two things you need to respect for free. So let's see if I can pull this off. So this would be something like A plus A prime. And this should be equal to what? Eventually, I want to show that this thing is an homomorphism. Help me someone. Yes, Manolis?
Phi plus psi of A plus phi.
Okay, so exactly. So I need to reach this. Can someone see why I need where the commutativity of the group B will be essential here?
Yes, because you will get like FA plus FA prime plus CA plus CA prime.
Yeah, so associativity will help you group the parentheses the way you like, but essentially at some point you will need to swap. So the intermediate step here would be something like, let's apply the definition. It's what? It's like phi to A plus A prime plus psi to A plus A prime. And now I know that each of these things is an homomorphism, so it respects these things. It commutes with the operation of the group. And I'm not using parentheses because I'm used to like associative structures like groups that I don't need to specify the grouping in parentheses. But the only way, the obvious way that I can go from here to here is if I swap this with this, right? So it's one more step that I need here.
You're missing an A prime there.
Yeah, probably. Where?
The last one. You're right.
Oh, yeah, thank you. So this is like phi of A plus A prime plus psi A plus A prime. So here is where I need, no.
I think you did this.
Yes, thank you. I undid the step. Yeah, you're right. Yeah, so I just need to. Okay, thank you. So I will not. I will do it the clever way. I will just need to swap two things. Let's see if it's clever. Okay. Is it that? Is this what I want? Yes, that's that. Yeah. So now it works, right? Okay. Good. So first moral of the story, took us 1 minute to do that. So do your homework at home. It's not so. Some things are kind of difficult, but some are like illustrative. So now you know why I want to focus in abelian groups, because I want to have like an operation. What I have defined here is an operation among the homomorphisms, specifically then also in the endomorphisms, since X is an abelian group. Now I have two reasonable operations, binary operations on these things here, on the yellow things. Composition, that has its own identity, and this plus thing, the addition. that I gain from the fact that X is an abelian group. And now you say, okay, so what extra laws can I infer from that? And have we written anything? No. Okay. So now you start thinking about rings, because you say, okay, I have studied very much like a structure that also has a multiplication under which it becomes a monoid, and you have this with composition and the identities, and you also have an addition, and you kind of hope that with this addition this becomes an abelian group, because if it does, it's a ring. Okay, so it makes sense to say, aha, what would be then a row from a ring, any ring I like, to this particular ring that I have here in the case that X is an abelian group. So you will have all of these things. You will not lose any of these things, obviously. I'll try to copy them here. So, but the thing that will change now is this thing that I have written here below. Okay, so this thing is now sigma will become a ring, so I will need further stuff. And let's see what will happen with this thing. So the further stuff I need is that it needs to respect the addition. So anytime you have like R plus S in your ring, this should be the row of R plus row of S. And you obviously need to map the 0 of your ring to the 0. We mentioned it the previous time, but I ended up erasing it from here. So with this operation, do you really have an identity? And is it really a group? I mean, with this operation that I just defined here, okay, it's a binary operation. So, okay, we will not do it now. You check it, it's associative, and it has an identity, which is the homomorphism that maps everything to the identity of this abelian group, to the 0 of B. And let's call it 0 for convenience, this constant function. And what are the inverses? So it's like, what should be the minus phi? It should be this thing that takes A and maps it where? So apply phi to A, you are inside B, and now take the inverse of B. Right, I mean, it's the obvious thing. So it is indeed a ring, and so I will map this to the 0. Maybe you want to make something, I will call it like the 0B here. Maybe you want to make this like boldface, I don't know. And then it's the row of minus R. This should be like the, well, help me here. Minus, so thank you. Row of R. Yeah, okay. So everything I have written down is a summary of something being a ring homomorphism. So nothing really has changed. I just have more identities here that I need to satisfy because my structure has more protagonists, more things. Okay. So, but what about this thing? So here I'm saying that I didn't have any further conditions back then when I was just in some arbitrary category of which I knew nothing about, because the codomain, which was like this thing, didn't have any extra structure that I needed to care about. But now I'm in the category, this C is the category of abelian groups, which means that I know that all these arrows need to be group homomorphisms. So I get some extra things that I need to satisfy. So let's write these things down. So what do I need to satisfy? Essentially what I need is that for each, okay, I will write it here, for each R in, since now I'm in a ring, I will call this R. In R, row of R is an arrow. So, but here arrow means group homomorphism. Okay, so let's break this down. What does it mean? Somebody help me. So rho of R is one of these things, right? So rho of R applied to, yeah?
A plus B will be rho of R.
Exactly, to A plus B needs to be rho of R applied to A plus rho of R applied to B. Let's go on. What else? Respect the identity and respect the inverses, right? So it's rho of R of, what's the identity here? The 0, okay? The 0 of B. Okay, sorry, I don't like, is it B? No, we have called it X, right? We might as well call it A to be consistent with these things. Okay, so rho of A, this is equal to, help me again here. It's 0 of A, right? Is that it? Am I correct here?
Is 0 of A on the left or is it 0?
That's what I'm trying to figure out because I'm in the group A here, so I'm looking at arrows from A to A. So it's the 0 of A, right? I think so. Okay, so let's see. And the other thing is minus A should be the minus of rho R to A. Okay, finally I'm done. Any objections? I don't like my lonely space, yes. Don't take it personally, yeah.
Before.
Okay, the same one, oh yeah?
Why do we have B on the left and A on the right?
Because, no, no, thank you. Suddenly, okay, this is what happened. I was talking about this operation that you can define on homomorphism from A to B as soon as you know that B is an abelian group. A doesn't really need to be an abelian group. So I had this B here that I was thinking, okay, I'm consulting the operation of B. But now, I'm looking at endomorphisms from abelian groups to abelian groups. So it means that, okay, instead of calling it B, I started calling it A. It's from A to A. It's the codomain, okay? So yeah, you're kind of right, it's a bit messy, but I think that if I fix this A, now I'm kind of consistent. It should be X, actually, but anyway. Okay, can we, yes?
You also have an X at the second line, which will also be A.
Thank you. Okay. So all these things, yeah, okay. So this thing will be, I will write like that, from A to A. Okay? Good. So this is no longer true. And actually the things I have I've gained because of this are all those new equations. For each row, for each R, I have these, okay? So how many equations do I have? It's kind of tricky. You say I have 3 plus 3. Actually, it's not this one, right? Yeah, because it's not a group, okay? So I have 2 plus 3, 5. And then it looks like it's plus 3, so I have 8. But I don't really have 8 because these are like a family of equations, one for each R. Okay, I have parameterized this thing for R. So for each R of your ring, you get 3 things you don't need to satisfy. Okay, and now here comes the tricky part, not so tricky actually, but shift of point of view. We know codification and carrying and uncarrying, sorry for this, which means that we know that from this we can view it like that, if we like. right? We know this, okay? And this means that instead of viewing this as a mapping from R to maps from A to A, you look at this like as if it was a binary function that takes an element of R, an element of A, and gives you back an element of A. I cannot call it a binary operation because I call operations things that are on the same thing. You give me a binary operation on which type, it will be on A, it's from A and A to A. So this, I will not call it an operation, but it's a binary function that takes this, okay, and then you say, I'm used to seeing infix notation for binary things, so let's try to do that. So let's try to translate these equations here in an infix notation. Let's call this some kind of multiplication, okay? So what will I have in the first equation? Essentially, these rows, these things that I have here will disappear. So I had here a mapping from A to A, and I had here a mapping from A to A, and I'm claiming that they are equal. How do I compare mappings? I need to give them an element, right? Let's call it, I don't know, A. So I will write this like that. I don't know how I should denote this multiplication, this new multiplication here. I will denote by juxtaposition. Okay, so it will be invisible. So if my invisible operation takes this element from R and this A from A, what is its obligation? Where should it map it to? Well, according to this, if you apply A to this, what do you get? It's the rho R of the rho S of A. But we don't like rows here. We like to see the infix notation, which gets rid of these rows. So how can I write this? Somebody? Yes?
S times A.
Yes, S times A, like invisible times, right? And how can I write now this thing apply to this? Just R times, okay? So I'm just using, this is nothing deep, I'm just using a different notation if I see this as a binary operation, which I can't see it as a binary operation because I have learned about clarification. So let's translate now all these laws. This would be R of S of A, and I will probably make a mistake and put a dot where I should put juxtaposition, and you will spot it. And this will be like what? The 1 of A should be A, thank you, which is the identity of A applied to A, which is just A. Now let's go on. The next one is and this is what? Okay, let's give it an A, right? And this means it will go like that and like that. So this will be RA plus SA. Is that correct? Okay, and this will be like 0A should be 0. And the next one is minus RA should be minus RA. I mean, if you start like that, you don't no longer even need to consult this, but please do, because what I'm trying to argue here is that we are not having inspirations here. We pretty much didn't have any inspirations anywhere. We started from a ring and another ring, and we're translating what it means for this to be an homomorphism. So we are just shifting notation. So even if you could infer like this from that, guess it, don't guess it, try to do it like that. Okay, so we have more. What's next here? Okay, so let's get rid of the rows here. Somebody? Yes?
R times A plus B is times A plus times B.
A plus B equals RA plus RB. And okay, R times 0 should be 0. And R times minus A should be minus R of A. Finally, I have translated all these things, which I got pretty much for free from one single word. Rho is an homomorphism from this ring to that ring. Okay? I got all these equations, I translated them in a different notation, better or worse depends on your purposes. And now I say, okay, what do I have on my table? If I have studied this, maybe it starts looking familiar. If not, I have discovered a new thing. Can somebody spot, I mean, does this particular set of equations, together with this type maybe, seem familiar? Oops, sorry, I hit them all.
It's a ring.
It's a, no, wait, it's a ring. No, wait. The ring is here. Where is it? Okay, it's not anywhere. The ring is like this structure set with 5 operations and 5 laws, essentially. Here it's too many things to be a ring. I mean, which one were you saying that's a ring? Because R is a ring, okay, we started from a ring, and A is some abelian group, and we are defining this weird multiplication here. Yes? Manolis, yes?
It's a module.
It's what we call an R module, right? It's an R module, and if for some reason, okay, I mean, if I call this a certain name, you will start making more connections. Let's call this multiplication scalar multiplication for some weird reason, and these things scalars. If I read and all the other things, maybe vectors or whatever, if I put some arrows, let's say, notational things, they mean nothing, okay? I'm pretty sure you have seen all these maybe you haven't seen modules, like, Manolis have seen them, you definitely have seen vector spaces, and this is pretty much all the equations you have in a vector space. It might seem random when you first see a definition of a vector space. Let A be some set and R some other set, and we have all these operations, and here are 12 laws. How many laws are there? Like, I don't know, 9 laws. Why 9? Because there is an extra one here, because instead of a ring, you have a field there, and it's the thing I deleted earlier. It's like, it's this one, right? You should get something like this, should be the inverse of this. And if you try to translate this in an equation, it would be something like, I don't know, figure it out. You probably get something more from the fact that, no, actually you only get this one. So what would this one be? It should be something like, okay, let's apply A to it and see. It's this one of A should be equal to the inverse of something, which means we will not manage to write this down as an equation. This will be something like an if and only if. Can somebody help me see this?
Would it be inverse of R applied to A is the inverse of I? I mean, yeah, you have to assume that it's inverse.
The inverse of A.
Inverse of R applied to A is the inverse of I.
You're saying that I can get it as an equation?
Yeah, but there may be some weirdness going on with stuff we didn't know to be zero.
Okay, let me check what I need to say here. Okay, the way I've written it here is that if this thing is equal to B, if and only if A is equal to RB. I'm not sure you can, I'm pretty sure you cannot write this as a single equation. But okay, let's make it pink. And this is homework to check. But does that make sense? Or does it not make sense?
Isn't the definition of the inverse almost?
Almost, but it's not exactly this, because this is not this is not the inverse. It would be the definition of inverse if it was an inverse with this operation. But it is actually the inverse of that ring, and now this operation is the juxtaposition. So you say that if if you take your ring, the R in the ring, and you invert it there, and you multiply it with the A, and this becomes B, it's the same thing. Then if you get this thing, don't invert it and multiply it with B, and this should be A. I'm confusing the thing too much, but I mean, if you write it down, I think it will be, you can only write it down like that. But in any case, you will get the connection with fields. Is there an extra axiom you see in vector spaces? You say that you can get inverses of these things. Where do you use inverses in vector spaces? I mean, do you have a specific law about these? I think you don't. You just say pretty much that if the ring on your module happens to be a field, you will call this a vector space. So
in vector spaces, we generally don't have inverses. Actually, we have inverses for the field, but we won't have inverses in the space itself. Here we have a group, so it's kind of special.
no, you do have inverses because inverses are the negation. It's an additive, it's in a group, so when we say inverses of the other thing, you do have the inverses there, and you do have all these laws that say things about these minus vectors here, right? So here, you do have the additive inverses, which are the negations. But this thing, I think you will not have an extra law for this. Anyway, it's not important for what I'm trying to say. The point of all this is like, you start from a simple thing, like you could now sum up the definition, the entire definition of a vector space or of R module to the following one line. It's an arrow from a ring to the ring to this ring. So you write this thing, okay, you would never define it probably like that, but I mean it's a very concise and very correct definition, and if you have this as a guide, it might also tell you that when you are defining something, you're probably taking a wrong route because it doesn't really make sense categorically speaking. I will leave you to check something, because when you define modules, you say left or right modules. You don't say that for vector spaces. And if you define actions, you say left or right action. And I mean, what's the deal with this left and right? Because it looks silly. If I come from this, this aspect here, it looks silly to say left or right. There's no side in any sense. So the homework here, I'm explaining it orally, is to figure out, okay, this definition that we gave, is it the left or the right? And if it's the left, then what do I need to alter here to get the right? And vice versa, okay? So, enough with this thing. We can take not a literal break, but let's take a break from this kind of heavy definitions thing. And I would like to see a bit of simple constructions in categories. So, okay, let's take a step back and let's see some more constructions in categorical constructions. So let's start with category C. This was actually homework, but I think nobody did it. So let's check it together. And pick an object C inside your category. And now look at all the possible arrows that land on C, that get inside C. So here is a blue thing. Here's an orange thing. We've done something simpler than that. So, since these are arrows, these are like some different objects here, like A, B, So it's X, some Y, some Z, I don't know. And all these things then are arrows that get inside C. And obviously, maybe what I want to do is see if I can get a category of the colored things, where the objects are the colored things. Okay, so the objects will not be like any arrows of my original category, but I fix a specific C object, and I'm looking at the arrows entering this object. And now the obvious question is, how do I define the things I need to define for a category? So I know that the objects are arrows that enter C in the original category. These are the objects. What should be the arrows? So I need to answer this question. What is, in this new category that I'm defining, what would be all the arrows from this to that? Do you get what I mean with this notation? I could use it like, there's also this notation, that's this collection of all the arrows that go from this object to this object, okay? So what would that collection be? What would be these arrows? Obviously, I don't want to define this in an arbitrary way. I need to consult the original category. So, ideas. We have seen something much more complicated than this. So I hope we can infer this. Okay, so what should get you from the blue to the orange? Manoli, you have an idea?
Yeah, they have the same domain.
What do you mean?
The same source.
I don't understand your answer, and maybe it's because I didn't express the question well. I'm trying to define a new category, right, among these things that are colored here. So this will be an object, this will be another object, this will be another object. My question is like, let's figure out what an arrow from the blue to the orange would be.
Yeah, they haven't, like...
What kind of things are they? Okay, so tell me.
There is an arrow or there is not, and there is an arrow if and only if they have the same source and there is no category.
Okay, so you could do that. That's a bit brutal, let's say, because you're collapsing many things, you're forgetting maybe too many things. You will essentially get a prosetter category 1 that either has a set or doesn't, has an arrow or doesn't have an arrow. It's just to check if pretty much these have the same domain. Okay, yeah, it would lead to a poset and therefore it will lead to a category. But it's like you start with a category and you say I can get a poset out of it. If you start from a category, you want to get to a category, you say I will reduce this to a certain kind of poset and now I will look at this poset as if it were a category. So you can do it, it works. But probably you have lost some categorical information in the process. So what would be a different way to go from this category to another category without like collapsing or deleting or losing this kind of information? Because supposedly, since you start with the category C, you care about the information that is within C, that is the object and the arrows of the C. So, okay, an arrow from the blue to the orange will be, let's start with an almost correct idea. An arrow from X to Y in the original category. Okay, so what gets me from the blue thing to the orange thing is if I have an arrow in the original category from X to Y. And since I'm doing category theory, I will not stop here. I will not take any arrow, but this arrow has to play well with the two arrows of the blue, with the blue and the orange arrow. So essentially, what will get me from the blue to the orange will be this commutative triangle. Think of it like a triangle that's somehow like kinda directed like that. It gets me from the blue to the orange. So and what would be an arrow from the orange to the purple? It will be another arrow that gets me like that. And now I have to ask myself, are the axioms of a category satisfy the laws of a category? I mean, okay, so if you have an arrow such that this thing commutes, and you have if you have an arrow such that this thing commutes, does that mean you have an arrow in the original category here that makes this thing commute, the big thing? So which would be the candidate arrow here? Yes? The composition. And will it commute? It will commute because you do two times the application of these commutativity triangles here and you get the commutativity of the big triangle. Okay. Do I have identities? So what's the identity arrow from the blue to the blue?
In the category.
What? Sorry?
X lives in the category, so...
I'm asking if I have identities in the new category that I'm constructing. In the original category, there was this identity of X, right? Guaranteed by the fact that the original C is a category. Now I want to see some from the blue to the blue. So it means that I'm looking for an arrow in the original category that is from X to the X. And Sotiri says, yeah, we have that because it's a category. C is a category. But it needs to make this triangle commute. So you say, aha, this is the arrow, and you claim that this commutes, and it does commute. Why does this commute? So the idea is that these things here are blue. And I'm trying to figure out if I can guarantee in this new category that I'm constructing something from the blue to the blue. Yes?
Blue arrows are equal, so
The blue arrow. What are you using? So I mean, yes, this is equal to this, but why is this equal to this? Yeah, you use the fact that this is an identity in the original category, so when you compose it with this arrow, look, this arrow is an arrow in the original category as well, so you compose this with this, you just get back this, which is this, and you're done. Okay. So you have an arrow, we have defined a new category, which is not so surprisingly if you see this picture, it's called the over category. As long as I pick a single object of this category and I see all these things falling to C, and I have a way to move around these things. Dually, there's defined the under category, which is of arrows if I want to call it an under category, I should respect gravity. So this is C. So now we have X, Y, Z, and what would be an arrow from this thing to the next. I mean, you guessed it, it would be like something like that makes this thing commute. So, as long as you have a category, you can define, and an object, you pick an object there, you can define a new category, which is all the arrows that get inside C, or get outside of C, two different categories. In the similar spirit, one more thing, out of a category, I wanted to find a new category. These two were homework, and I think it would make more sense if you had worked on them. So here I have an original category C, and I want the objects of the new category to be any arrows in C. I don't want to fix an object and say arrows getting out or getting in. My original category was like that. I don't know. Now I want the object of this new category to be all the arrows. So the obvious question here, again, is how would you define a way to get from one arrow to another arrow? So you have, in particular in your category, like this thing, and you have this thing, and the question now is how you go from the blue to the orange. You want some way that will get you from here to here. Any ideas? Manolis? It's a pair of arrows, a couple of arrows. One from A to C, and one from B to D. And I hope we are getting the idea that we'll not stop here. Such that this square commute. So the previous thing, you can think it as a triangle that is kind of directed, right? It's this thing. This thing is an arrow from here, and this thing is an arrow from this thing. Visualize it like a triangle that goes like that. And this thing, you will visualize it now as a square that goes, I don't know how to draw this well, but like that goes this way. Okay, so visualize, it's like this. The whole square. And what do you need to check are their identities. What's an arrow from the blue to the blue, and why is it guaranteed to exist? Obviously, you will be here. You have A, and here you have B now. So, which arrow will you get here? The identity of A and the identity of B. And does it commute? Yes, it commutes because you apply the identity laws in the original category. And what about composition? So you have A, B. Terrible letters, C, and here you have A prime, B prime, C prime. So if you are like that, and you have this arrow, right? This is an arrow, and this arrow here. Why do you have an arrow here? I mean, these two squares commute, therefore this rectangle commutes. So the arrow you have is the composition of these arrows with the composition of these arrows, and now you have an arrow from this to that. Does that make sense? And we call this, and with the arrow category of C, we denote it like that, and it's a good time for a break. Let's do.
Να ρωτήσω κάτι. Έχασα το σημείο εκεί πέρα που κάνετε από το
Έκανα.
isomorphism, το σημείο
Ποιο?
που είχατε από το R στο A to A και μετά το κάνατε RA στο A, την πρώτη σχέση για πώς αιτιολογείται το δεξί κομμάτι.
Αυτό.
Ναι.
Οκ. Αν πάρεις αυτό εδώ, αν πάρεις αυτό εδώ και το αναλύσεις, τι λέει. Καταρχάς,
Καταρχάς πρέπει να έχει αυτό το α εκεί.
μπράβο, λοιπόν, να δούμε τι σημαίνει. Ουσιαστικά, Μαλώνα, μπορείς να ανοίξεις την πόρτα, please. Κάποιος μπορεί να θέλει να δει κάτι. Τι είδους πράγματα είναι αυτό?
Ένα στοιχείο.
Ποια...
Είναι η εικόνα στοιχείο.
Όχι, μισό. Αυτή type of thing είναι αυτό. Το ρο παίρνει πράγματα από εδώ και τα μεταφέρει εδώ. Άρα έχει πάρει αυτό που ήταν εδώ και το έχει μεταφέρει εδώ μέσα. Που σημαίνει ότι το αριστερό μέρος της εξίσωσης είναι κάτι από το μεγάλο A στο μεγάλο A. Και εδώ πέρα επίσης είναι. Καταρχάς, άμα δεν ήταν, θα είχαμε type error. Πάμε να πούμε ότι είναι ίσα πράγματα που δεν είναι. Άρα και τα δύο αυτά είναι elements of this type, ας πούμε. Okay? Ωραία. Τι σημαίνει ισότητα σε αυτό το type? Αφού είναι συναρτήσεις από το A στο A, μεταφράζω το τι σημαίνει ισότητα σε συναρτήσεις. Σημαίνει ότι για κάθε x ή για κάθε μικρό a συμφωνούν. Αυτή, άμα την κάνω apply στο a, θα είναι ίση με αυτή, άμα την κάνω apply στο a. Ωραία. Οπότε το γράφουμε αυτό κάτω. Το γράφουμε κάτω. Καλά, μιλάω κάτι ελληνικά υπερβολικά όμορφα. We write this down. Okay. Το δεξί μέρος τώρα κάνω απλά apply το τι σημαίνει το composition. Είναι το ρο R applied στο ρο S applied στο A. Το οποίο του κάνουμε apply το μέσα του τι έχει. Άστο αυτό. Μεταφράζω τώρα το συμβολισμό του, τον infix συμβολισμό. Αντί να πω ρο του S στο A, αυτό είναι που έχουμε βαφτίσει SA.
Έχουμε βαφτίσει SA.
Ναι, είναι αυτό ακριβώς που έγινε εδώ. Στο juxtaposition. Ουσιαστικά τι σημαίνει...
Αυτό το κομμάτι.
Αυτό είναι το purification που είπα πριν. Αντί να θεωρήσεις ότι έχεις το ρο που σε πάει από το R σε κάτι το οποίο περιμένει ένα argument για να σε πάει από το A στο A, λες αυτό θα το ονομάσω... Νομίζω έχεις δίκιο ότι αυτό δεν το έγραψα καν και γι' αυτό το έχασες. Εδώ είπα απλά... Μπράβο. Εδώ κάτσε να αναλύσουμε λίγο αυτό το purification. Αυτό λοιπόν ορίζω σαν RA, το ορίζω αυτό να σημαίνει το ρο του R στο A. Ουσιαστικά, το shift στο mentality από το operation το εξής. Όταν σκέφτεσαι έναν διανασματικό χώρο, συνήθως λες, έχω ένα binary operation, το scalar multiplication. Δώσε μου scalars και δώσε μου τέτοιο. Άρα σου ρωτάω πόσα operations έχει συνολικά, μου λες, έχω ένα scalar multiplication, ένα vector addition κτλ. Και σου λέω, μισό λεπτό, δεν θέλω να μου σκεφτείς ότι έχω ένα binary scalar operation. Μπορώ να σκεφτώ ότι έχω άπειρα unary operations, ένα για κάθε πραγματικό αριθμό, πες. Οπότε δεν το βλέπω πραγματικός αριθμός επειδή άνισμα κάνει κάτι, το βλέπω, κάθε πραγματικό αριθμό τον βλέπω σαν συναρτησούλα που παίρνει μονομελή συνάρτηση, που παίρνει ένα vector και επιστρέφει τον πολλαπλασιασμό του με το R.
Σαν τη γραφική άλλη που έχουμε τις συναρτήσεις LA του α που είναι LA του β που είναι α επί β.
Ναι.
Ακριβώς. Οπότε ουσιαστικά αντί να σου πω πάρε μετάφρασέ μου τον πραγματικό σου αριθμό βάζοντας το R, στη συνάρτηση, τη μονομελή συνάρτηση που κάνει transform as vectors, σου λέω, ας το πούμε όλο αυτό το transformation, ας το γράψουμε R επί A. Το R επί A, αυτό βελάκι δεν ξέρω αν βοηθάει. Τι σημαίνει να πολλαπλασιάσει το R επί A? Δώσε μου αυτό το μετασχηματισμό που αντιστοιχεί στο R, δώσ' τον μου, τον πήρα, και τώρα κάνω τον apply στο A. Okay.
Συζητήθηκαν σε κάποιο λέξο αυτό που πιθανώς να έχασα.
Μάλλον όχι. Αυτό που μόλις είπα τώρα, όχι, το πέρασα εγώ τώρα αυτή τη στιγμή ίσως εντελώς invisibly με το που είπα έχουμε το purification και νομίζω είπα κάπου εδώ.
Στο τέλος του προηγούμενου,
μπορεί...
μετά που είχαμε
Αλλά μήπως το είπαμε δυο μας και έχω την εντύπωση ότι το είπαμε όλοι μαζί.
Νομίζω πως το έχουμε ξεκινήσει το ψιλολέγαμε. Εμένα αυτό που με έχει τελικά να καταλάβω πώς δουλεύει αυτό είναι ότι ουσιαστικά όταν κάνεις αυτή τη διαδικασία, δηλαδή αυτό το οποίο πάει πράγματα της άκυρης ομάδας που έχω, σε
Το άκυρο ring.
μορφισμούς, ξέρω εγώ.
Το άκυρο ring που έχω, της ομάδας μας. Οκ, αχα.
Λέμε ρο, πι,
Λέμε...
είναι πι αυτό, δεν είναι ρο.
Όχι, είναι ρο, δεν βλέπεις, είναι κυκλικό. Συνήθως ομολογισμούς του γράφεις με ρο, φι, ψι, ελληνικά γράμματα. Γι' αυτό το γράφω ρο εκεί. Δεν το έχω δει ποτέ πι.
Όταν κάνουμε ομάδες, γιατί όταν κάνουμε ομάδες, ουσιαστικά έχεις αυτή τη ρο, η οποία σου πάει, ξέρω εγώ, την άκυρη ομάδα που έχεις, στην ομάδα των αυτομορφισμών του αντιφράγου αυτού που είχες. Οπότε ουσιαστικά το ρο ενός στοιχείου R, τι είναι? Είναι κάτι που μοιάζει με το. Είναι ένας μετασχηματισμός πάνω στο αντικείμενο εκεί, που μοιάζει με το R. Πρέπει να πω, παίρνω αυτό που μοιάζει με το R, τη συνάρτηση που μοιάζει με το R και το εφαρμόζω στο Α, λέω ότι εφαρμόζω το R στο Α. Παίρνω ένα αντίγραφο της ομάδας που είχα αριστερά μέσα στους αυτομορφισμούς.
Το οποίο το λέμε group action. Δηλαδή, group action. Το bottom line είναι. Μισό λεπτό. Το bottom line είναι group action, ring module και vector spaces είναι όλα το ίδιο πράγμα. Με την έννοια ότι όλα ξεκινάνε από το εξής. Να δώσουμε ένα όνομα σε ένα βελάκι από group, monoid, ring, pick your favorite, στους ενδομορφισμούς του X. Άμα είναι group, το λέμε action for some reason. Άμα είναι ring, αντί να το πούμε action, δηλαδή ένα άλλο όνομα για ring module θα ήταν ring action. Και ένα άλλο όνομα για vector space θα ήταν field action.
Πολύ καλύτερη αυτή η ονομασία.
Ποια ή?
Αυτή είναι πολύ καλύτερη η ονομασία γιατί καταλαβαίνεις κατευθείαν τι γίνεται.
Αυτό το point, οκ.
Okay.
Ήθελα δηλαδή εκεί πέρα να πω ότι όταν το δεις αυτό μπορεί να πεις είναι ο χειρότερος ορισμός που έχω δει ή να πεις ότι I appreciate it, ας πούμε, έχουν έρθει όλα στο ίδιο καλούπι. Αυτό νομίζω λες. Okay. Αλλά και το άλλο δεκτό είναι. Κάποιος να σου πει γιατί να βρούμε το κοινό source που έχουν αυτά τα τρία. Νομίζω ότι όταν το βλέπεις είναι κάπως enlightening, ας πούμε, και λες OK, τώρα γιατί το λέμε action. Και μένει ακόμα να απαντήσουμε το left and right. Αλλά θα σας αφήσω να το σκεφτείτε αυτό. Δεν είναι κάτι deep. Αλλά ουσιαστικά έχεις left actions και right actions. Και έχεις left modules και right modules. Κάπως εμείς έτσι όπως το ξεκινήσαμε είναι σαν να έχουμε κάνει favor κάποια και σε φάση τι θα έπρεπε να αλλάξω για να ανακαλύψω τα right, αν είχα τα left, ή τα left, αν είχα τα right. Κάτι πρέπει να αλλάξω εκεί. Okay, so we have seen like 3 new constructions on categories. It's the over, the under, and the arrow category. Now, in a similar spirit, there is one that's extremely useful and common, is the Okay, so we have seen more or less that we can have a category of categories, and I will call it like cat, where the objects are categories, and we have figured out what the arrows should be. It were functors. We haven't verified, this was homework, and I think nobody did it. It's very simple that indeed these two form a category. I mean, why do functors is a correct notion for an arrow for a category? I need to check that I have identities. So what is the identity functor? I'm in side C, and I'm wondering of all the end of functors, which should be called the identity functor? And I think it's pretty obvious. Let's call it I. How it acts on objects, the I of A should be A, and how it acts on arrows, the I of F should be F, okay? And you check that indeed it's an identity, and the other thing that you need to decide is how you compose functors. So if you have like from C to D to E, and you have a functor F and a functor G, what should be the composition of these two functors, which I'll write like that. And obviously again, this thing, when it acts on an object, when applied on an object A, this should be just G of F of A. And similarly for the arrows, and what you need to verify is that all the laws are satisfied, and they are. So essentially you realize that Indeed, you have a category of categories, and the functor is the correct notion for an arrow. And now we have also met ways to go from functors to functors. Does anyone remember what this thing is? I mean, we haven't worked with it a lot, but we've defined it. How do I go from F to G? If I fix two categories and I look at all these functors from C to D, what is a way that gets me from one functor to a different functor? Aha, okay, so this is the natural transformations, okay? So we haven't seen many examples from this, but we have defined it, and this means that I have a good candidate to check if I can form a category on functors from C to D. I will denote it like that. So now the colorful things that I want to be the objects of the new category will be, let's say, this and this. So what will get me from the blue to the orange? It will be some natural transformation alpha. And we can remember how we defined the natural transformations. It was around here. Okay, it looks kind of complex, but I mean, if you think about what's happening, is you have so this is your category D, and you have some other category C here, and you have mapped it in a blue copy of itself and in an orange copy of itself, and you want somehow to transform the blue image to the orange image. I think I said yellow, but anyway. So in order to do that, you need for each object here to tell me how to get to an object there, and you have to do this in a way that these things commute. So it's pretty much the only thing you can write down. It may help. At this point, I have 50% of the class are like math department students, and 50% of the class are computer science students. It might help to see maybe some kind of example of what a natural transformation would be in programming terms. So we have met some functors in programming, examples of functors in programming languages. The first one I think was like list. And the idea of list is that I can apply it on types, like list of alpha is a new type, and I get back types. And I can also apply it on functions from alpha to beta, and this, so if I have, the idea is that if I have f that goes from alpha to beta, I get the list of f, which is usually called f map or map of f in functional programming terminology, that gets me from that to that. And this is like the obvious thing you would think of if you have a function and you try to apply it in a list of things. I mean, that's what you would do. You would apply it to each element of the list, and you'll put these all elements together. And the functor laws force you to not mess with this shape of this thing. So it's common to think of functors as some kind of shaped values, or some kind of wrapped values, or some kind of, I don't know. There is usually some computational content to this when we're doing programming. Like, I can give like an example. If you think of a list, you can think of a list as a value that changes through time. So if you have like, I don't know, this list of natural numbers, it could even be infinite, I don't care. If you have this list, you can think of it, it's a natural number. It's like maybe, I don't know, the position of something, or the temperature, I don't know. That changes every day. So you can think of it like that. And the idea is that, okay, if I know how to sum these kind of things individually, I should be able to infer some kind of computational thing, a computational interpretation of what it means to sum this moving through time value with another moving through time value. Obviously, what will be the value of this thing on the first day? Look at the two values and sum them. And on the second day, look at the two values and sum them. something like that. And so you do have this functor here, this list, and it will never happen that this thing will change. You will change like the form of the list you are applying. You get from a list to a list, you will apply the function, so the function will change the elements inside the box, inside the list, but it will not change the number of the elements of the list. You will not apply an f map of an f, a list f, on a list with 3 elements, and then get a list with 2 elements. This will never happen. Does that make sense? So in a way, the laws force you to don't mess with the structure, update the values there, change the values that you will find inside this thing. Maybe it's not a list, maybe it's a tree. So like, if it was a tree like that, and I apply like the doubling function on this tree, even if I don't want to do calculations, I know from the functor laws that the output will be a tree of this shape. It will not change the shape. It's like, okay, it will be 3 here, it will be 1 here, 2 here, 7, and okay, I'm not doubling anything. So this was the identity, sorry. It's like 6, 2, 4, 14, 16, okay? But you will never apply a proper functor on this thing, the list thing, on this tree. So not the list, sorry, the tree. You will never apply a 3f on this thing and get a tree of a different shape. It will be this shape where everything, you will just apply f to all those things, respecting the overall structure, okay? I hope this makes sense. And, okay, another famous functor, it's the maybe one. Maybe it's time to talk about this. I think 50% of my students know this, and 50% of my students don't. Am I right? From the faces, yes and no, right? Yeah, right? Okay, so let's try to define this. What is the maybe alpha? And we'll see how we can do it in a much simpler way. But usually it's defined like that, or sometimes called option alpha or maybe alpha. And the idea is we want to capture what's the programming idea here. I want to capture the idea that maybe, sorry for the word, I can have a value of A, or something failed, I don't know, and I don't have anything. So think of like you have partial function from alpha to beta, and so you want to apply, it's a partial function from alpha to beta, you want to apply this function on a value A. So what's the type of this thing? It may be undefined, we say, right? So instead of doing that, you can think of f, say, okay, I will actually have an f, I don't know, hat, that goes from alpha to maybe beta, and I still haven't said what maybe means, and now there are 2 kinds of values inside maybe beta. It's just the beta values, or something that represents the nothingness, that's something undefinedness or something was wrong. So I will define right now quickly this maybe thing, and okay, so let's define it the way we are usually defining types. So what are the constructors of this? It has something that we'll call just. I'm following kind of Haskell terminology here, but it's pretty standard. And the type of this thing, you give me an alpha, sorry, and I give you back a maybe alpha. Since these are a maybe alpha. Since these are constructors of this type, I know that all the constructors I will write will have maybe a bunch of arguments, but essentially they will end up constructing something of this type. So I will never write something here like, I don't know, to nut. It doesn't make sense. I'm listing the constructors of a type. They will end up eventually, if they get all the arguments they need, to something of type this, and it's nothing here. And this is immediately a maybe alpha. So let's see an example, and I don't have any other constructors. So for a type, let's pick a specific type like nut. What are some values of maybe nut? You may be tempted to think that it's 3, 4, 5, and also something that represents nothingness, like nothing, I don't know, and also 8, and an infinite number of things. Why is this wrong? Yes?
It should be just.
Exactly. Thank you very much. So now I have 100% of the class with me. Right? We agree? Okay. All these things are type maybe not. Okay. So the whole point. So if I have a computational interpretation in mind, it's a value that maybe didn't work out, and I don't really have a value, but I want to keep using that. Like apply a function f. Let's take the double function. Okay, so the double function. The only problem I have with the double function is that it's an endo function, so it goes from nut to nut. Maybe I could do something is even that goes from nut to bool to see if maybe is actually a functor. So if maybe is a functor, first of all, I know how maybe acts on types. It gets a type and gives me back this new type, the maybe alpha. It gets an alpha, it gives me maybe alpha, which is a new type. So indeed, it's from type to type. And now I want to see if I can shift this to also be applied to functions. So here I do have this function, and I'm wondering if I can infer from this something that goes from maybe not to maybe bool. And this will be like the maybe even. In Haskell, we would write this like f map of even. But okay, let's respect this idea that I have the same thing that I can apply it on objects and on arrows. So how would the maybe even be defined? I mean, if you try, let's try to apply this function on this value. I will test Manolis since he is the beginner here in this thing. So what do you think the output would be? I'm applying this new function. I haven't defined it yet, okay? But I'm trying to see if I know how it should kind of behave with examples. So if I apply this thing to this value, first of all, is it the correct type of value? It should get maybe nuts, and it got a just 3, which is a maybe not. So, okay, the input is okay. What the output should be? Which is?
Just true.
Yeah, no, 3 is not even. We have bigger problems. Okay, so it's like just false, okay? And you imagine what will be if I apply this to just 4? And what will happen if this is like, if I apply this to nothing? Nothing, right? We agree, Lazarus? Okay. So let's try to define this in the abstract way. It means that you have an f from any alpha type to any alpha beta type, okay? And now you want to define what the maybe f will be, where you go from maybe, it has to go from maybe alpha to maybe beta. Why does it have to go from maybe alpha to maybe beta? Because I'm supposed to be defining a functor, and functors have to respect sources and targets, obviously. So what would the obvious definition be? I will define it, okay, I know it goes from there to there, so I will define it by pattern matching, which means I will see all the possible forms that my arguments will have. All the arguments I have, it's either just of something, or it's just a nothing, sorry for the words. So I can say, okay, in case it's a just of A, and with these two equations, technically the first one is not only one equation because it's polymorphic, parameterized from this A. It's for each A, I have this equation, and here it's the nothing. Okay, so I need to produce on the right something of type B, okay? And maybe I should decorate this to say that this is the nothing of the maybe alpha type, the just of the maybe alpha type. So one easy way to produce something of maybe B is just say nothing. Okay, so this will type check, but it's obviously, it will break some of the laws that I have. So the obvious thing to do here is that in this case, I indeed got a value. So I will apply the function to this value. It's applicable. So this will be something like and here this will be something like this. So if you get a value, look at this value, apply the function to this value, and then wrap it again with this just constructor, and now you have a maybe b, and this is the obvious return thing you should return, right? So kind of rushing a bit here, but I hope, okay, so sorry, I'm not done because I need to verify that this thing that I'm defining is indeed a functor, which means it respects the two laws that it needs to respect. So which are the two laws? It needs to respect identities and compositions, which means that the maybe of the identity should be the same thing as the identity, so, but be careful, the two identities on the left and the right are different. On the left it's the alpha, and the right is the beta. And you check this and it works perfectly, and it's the same thing with this thing. If you apply this, this should be the same as this. Did I write it? Yeah, I wrote. Yeah, it's, no, is it correct? Yes, correct. Okay, this worked out well. So you do have a functor, and now I have two examples of functors. And I could also mention like a tree, but I think we will not need to do that. You can think of a tree as a type. There are various trees. If you look at the forms, they will represent things like that. But okay, let's leave trees for the time being. Let's focus only on lists and maybes. So one observation about the maybe type is like I'm not really doing something new. In the type theory we have so far, we already had maybe, and maybe you cannot see it. Manolis, if I ask you like, so far, did we have a way? So actually the question is for both of you. Before like this lecture, did we have a way that we could get an F or get the idea of a type, and now based on this type, get the idea of values that could be of this type or not at all, like or no value at all? First of all, does my question make sense? Like, could I capture the idea of something it's either a natural number or absence of this, or some kind of error or whatever? Yes?
We had the type addition. So
which one do you mean?
we could add two types to get a new type.
Something like
An either.
yes, but we haven't seen either. What have we seen that we can use like that? Yeah.
The addition.
The sum. Okay, sorry. I got what you mean. So, how will you use addition in order to capture the idea of maybe?
We basically construct the type nothing for nothing. It's a type with just one element.
And we have it.
Yes, anyone.
We do have this type, like the unit type. Okay.
Yes, but.
Okay. Yeah. Would you like a different name? And I agree completely. We should have a different name.
Add it with whatever type you like to get.
Okay. Very nice. So whatever the programmer is doing in Haskell, like with maybe thing, we say, okay, good names, we like them, we could copy them as well so that we think in a similar and consistent way. But essentially, alpha plus one, this type that we already know what it is, can serve as a maybe alpha. We could say that maybe alpha is like just I'm defining maybe alpha to be this thing. But I mean, what Lazarus is saying is extremely important. It's very easy to not appreciate this, that the names matter. So how you will call, okay, so this is like also a good intro for the next lecture where we'll see the importance of those things. But when you have alpha plus beta, you know that, when you have alpha and you have beta, we know that we can form this product, and we know what in category theory means to be a coproduct, or sum, what it means to be a sum, and it means it has a universal property that tells you how you can get out of this thing, and to define maps on any other candidates for products, but in order to be a candidate, for sums, in order to be a candidate for a sum, it means that you come together with two also ways to go from here to there. Okay. And we have proved, I think, even together, it was a homework, but it's an essential thing, so we did it, the uniqueness in categorical terms of products and coproducts and all those things that are defined with universal properties. So essentially, for the category theorists will say it is the sum of alpha and beta, and the product of alpha and beta, right, in quotes. We know what this means is that any two products or any two sums are isomorphic. And now I want to emphasize why you may care about having a bunch of them, even though they are isomorphic, and not just one and eliminate the others. Because it makes a huge difference how you call these arrows. So if you want to say, like, if you think in terms of proving or programming, which is the same thing, you need to have good names to help you think of these things. And so it's different if I say something like, if I give this name, okay, the names we used here were generic, was like in left and in right. Good names because they are generic, very bad names if you want to associate a certain behavior on what it means that it's an alpha and what it means that it's a beta. And if alpha and beta are different types, you may think that it's okay, I will infer it from the fact they are different, but alpha and beta could even be the same type. So, for example, imagine that it's integers and integers. So you have this thing, and now you get to choose to tell me which of the sums of integer types you are thinking about. So maybe the application you're thinking, okay, let's think of programming terms right now. Maybe the application you are thinking to represent, the idea you want to represent by this thing is that, I don't know, you're querying some kind of shop online and you want to know what the customer ID is, okay? And you represent, for some reason, customer IDs by integers. So it could be the customer number 42. But maybe when you try to capture this idea, like what is the customer ID there, actually an error happens, okay? Because the database is down, because you don't have permission to know that. Any kind of error thing can happen there. And for some also bad reason, but bear with me, you represent your errors by integers, like, you know, the famous 404 error file not found, permission denied 403 or whatever. So it would be very different if you have the client 404 or if you have the error 404, right? On the first option, it means you have a client, it happens to be the 44th client, and the other thing is like you couldn't find some kind of error, okay? So it would be very bad if you're programming and you're defining a new function depending on what you will see, and you will say, if it's an in left of an x, then you will do these things, while if it's an in right of an x, you will do those things. Because now what is in left and in right? You will need to remember what kind of convention it was, whether the lefts you think them of as valid values and the rights you think them as error codes. So no, I mean, you will say in this case, I will call this like client ID in my silly example, and I will call this like error code. Okay, too many R's, error. So now your proof for your program becomes extremely much more readable, because here you will say if it's some client X, it will be that, and if it's an error X, I will do that. Okay, so it makes a huge sense if you are a human, which of all the infinite products you have, you will pick. So my point here is that then we used to say, I mean, when you're doing only set theory, maybe you say the only thing that matters in a function is the graph of the function. You kind of identify functions with the graphs. And then you're doing some category or type theory, you say, okay, this is a very bad idea. Part of the data of a function is also its domain and its codomain. And even the set theorist maybe can say I don't need the domain and have the same information, because you can infer the domain of a function from its graph, but you can never infer the codomain. So, like if you ask a set theorist, is this function injective? They understand the question and they can reply. They look at the graph and they see if they are collisions, like these two things got mapped in the same thing. It doesn't make sense for a set theorist to ask them, is this function surjective? Because what is the codomain? If you look at the graph, you have to ask them, is this on to that set? And give them a superset of the range. They can only see the range. They can only see the values that are actually output of this function. Maybe you're considering a constant function from R to R. They cannot see this thing if you are doing set theory as you usually do. And then you say, aha, so it should be a triple, like a set, a graph maybe, and another set, and all this triple, it's the data of a function. So right here, I'm kind of arguing, introducing the idea that maybe there is a fourth thing that makes part of a function, that's the name of the function. We're getting a bit too philosophical, maybe too intentional, but it makes sense to say, wait a minute, will you program with this or with that? And if I say that I cannot see the names, it will not make any, I cannot argue that this thing is better than the other thing. So essentially, I'm kind of saying, let's look at the names as well to say this is better than that. Because if you hide the names, I'm looking at the same thing, okay? So back where I was trying to get to is now that we have two examples of functors, the list and the maybe in programming, let's see what it means to have a natural transformation from the maybe to the list. So what would be something that gets me from the maybe to the list, or from the list to the maybe? I don't know. Let's do the list to the maybe.